So it's time to start particle mechanics, linear momentum, and this will finish the topic of particle mechanics. So let's see what we have thus far. We've done Newton's law. Okay, we have that right here, and we've looked at the energy equation, which we have here. Okay, so now it's time to move on to momentum, which means we're going to take that the force equation and we're going to integrate it. Okay, so we take this equation here, we're going to integrate it, integrate ma, so we obviously, the mass is constant, so we wind up with v2 minus v1, and you recognize these as momentum. This term over here where we integrate the sum of forces, all right, that's called linear impulse. We put an L to that typically, okay? So, and if we look at that, so what that's telling us is that if the integral of the sum of the forces is 0, well, we'll put a 0 over here. It basically says v2 equals v1, and that would mean that momentum is conserved. Now, if you kind of look at this equation, you can see one of the clues of how do you know you have a momentum problem. So you see the time in here and the velocities over there. When you see time and velocity, it's usually a pretty good clue that it's a momentum problem. But momentum can be triggered by other things. If you have a problem where it talks about the impulse, bam, you know you've got a momentum problem. No other way. And then there's a third clue that shows you have a momentum problem. We're going to get to that in a little bit. And that's where you have impact. So think kind of like pool balls coming together and crashing. All right. So we're going to take a look at our first problem. And that's going to be the following. And so what we're looking at here is a rock, a 100 kilogram rock, so pretty heavy if you were to look at it from a weight point of view. So we have its weight, we have the normal force. The surface here is smooth, okay? And it's being pulled along by a 200 Newton force, which is at 45 degrees to the horizontal. Okay, so the 200 Newton force is not enough to lift it, but the x component will slide it along. So our motion will be in the x here. So we're told in this problem, here's our rock, 100 kilogram, here's the force, and it's pulled for 10 seconds. Okay, and that takes us to the second state, starting from rest. What is v2? So our clues here, we have time, we have velocity. It's a momentum problem. So the first thing we're going to do is just write down our basic momentum equation. We're integrating the sum of forces. And so if we take that along and just substitute in, obviously when we integrate this, we get mv2 minus mv1. So 10 seconds, the forces along the x. Okay, this is a vector equation. We put a little bar here too. So we're taking it along a given direction. Okay, it's not a scalar like when you have energy. It's vectorized. So we're going to take this along the x. So the summing the x forces, integrating over 10 seconds, takes us to mass times the second velocity. First velocity is 0, so it's kind of boring. That's a really simple integration. So 200.707, these are constants, so you just have a 10 that comes down, equals 10 v2. Solve for v2, and you're all done. So we're going to do another problem. And for this one we have, this will be another momentum problem, which isn't surprising. But what we have here, pulley system. All right, whenever you see pulley systems, we have a bunch of assumptions. One of the assumptions is typically that the pulleys and the string are massless. Okay? So we also will assume that the rope is not extensible. So it's not elastic. Doesn't grow, doesn't shrink, what have you. So we have this rope, comes down, goes over pulley D, comes up to pulley C, around it, and then hanging down to mass B. So we have mass A at 3 kilograms, mass B at 5 kilograms. Again, we're starting from rest. And what we want to find then is velocity A, velocity B, also a tension, and there's force in that our momentum equation, at t equals 6 seconds. But we're seeing a lot of velocity and time, and so as you see problems through the semester, that's usually a momentum clue. All right. Now, notice I have a little comment here where I say assume the pulleys and string are massless, and that says the tension is constant. Well, let's just comment where that comes from. So if I have a rope, so this is my rope here. So we'll put some strands into it. All right. Now, if I put a force over here and a force over here, say tension 1 and tension 2, okay, and I'm going to assume that this is massless, m equals 0. Well, that says the sum of all forces equals ma. Oops, forgot to put the f. If mass is 0, that makes this whole side 0. It means the sum of the forces must equal 0. So if you have a massless string, the tension has to be the same everywhere. You can't avoid it. All right, that's what that's getting at. And that'll be pretty well the normal case that we have. All right, so we're going to start to evaluate this thing. And how are we going to do that? So here's the main rope that we're going to be concerned with. So here we have off this pulley a second rope. It'll have a tension, obviously, and it's holding this box. So what I want to do is take the information here and kind of propel it up into this rope so we can solve this thing. So I'm going to start here and do free body diagrams and figure out what's going on. So here we have pulley D. If I were to cut the rope there and there, I have two tensions. The tension, because it's a massless rope, is the same everywhere, so I have two TBs. And then this other rope, which I really don't care a lot about, I'll call that tension A coming down. And if I sum the forces, because the mass, this pulley is massless as well, we're left with 2TB minus TA equals 0. So the tension here is half the tension there. Okay? So that's kind of boring. We'll just move on. And we'll take a look at, go down to there. So here I have this tension relative to this box that's coming up. And then here's the weight, 3 kilograms times gravity. And so I'll sum the forces. TA minus the weight of the box will be 3 times the acceleration of A. Now note, I don't really care all that much about the acceleration of A. And quite frankly, I don't care all that much about TA. This is just a little isolated rope. I want to get rid of it. So I'm going to replace TA by 2 tensions B right here. Okay, this is the sum of the forces. I don't care about acceleration, so I'm going to ignore this side. I'm going to take this piece, and then I will put that into the momentum equation. All right, so I have mass of A, its initial velocity, well, that's going to be 0. This sum of forces, I just pull that right down into here. Now I have to integrate it. These forces are all constant, so that just means multiply by 6. Stupid simple integration. And that's 3 times VA2. All right. Oops. So now we'll move up and take a look at TB. So let's see, bring that down here. So here's box B. We have the tension coming up, the weight going down. So we have TB minus its weight. Same idea. Starts from rest, summing the forces, TB minus the weight of the box. 6 seconds, simple integration, equals 5 VB2. Now what do we see here? When we look at this problem, what we have is TB TB is an unknown, VA, VB. We have 3 unknowns, or variables, and 2 equations. We need some more information to solve this problem. All right. So where are we going to get that extra information? Well, let's pull this over just a little bit. So here's this pulley system, and one of the things that you'll recall from Eng 1082 when they did pulley systems in kinematics was that one of the tricks to dealing with a pulley is to write an equation based on the things that can vary and set it equal to a constant. What am I trying to say here? If we look at the length of this rope, the length is constant, all right? And there's certain things about this rope that are boring and we're going to ignore. So you have it hanging, here's the point where it's pinned, so I don't need this distance. It never changes. Okay, I have this distance, that can change. This distance around pulley D, fixed. This distance can change. It's the same as that one. So measuring down from this point down to right here in the pulley, I have SD here, SD there. Continuing looking at the rope, going around the pulley, never changes. So it's boring. Now we have the rest of the rope, and so I'll call that SB, measuring from here down to there. And so we can now write the following equation. This distance plus that distance plus that distance, 2SD plus SB, is a constant. All right? The rope is a constant length, but I'm just going to deal with this distance, that distance, and that distance. I don't know what this distance is around these pulleys, and it doesn't matter. It doesn't change. So I'm just going to look at the things that can change, and they've got to sum up to a constant. SD plus SD plus SB. All right? Why do I do that? Because when I take the derivative of these things, I get 2 velocity of D plus velocity of B equals 0. That constant just goes away. And I could do it again and get acceleration. So what I have then is VD equals minus VB over 2. All right. Now, I'll also note that this D here, velocity of D, is also the velocity of A, because we're supposed to get the velocity of block A. So whatever D does, A does the exact same thing. All right, so if I stick that in, I have 2 velocity of A equals minus VB, or VA equals minus 1/2 of B. And that makes sense, because if I take any of this rope and move B up, half the rope goes here, half the rope goes there. So this only goes half as fast. All right, so that's my other equation right here. I needed one more equation, and once you have that, you can solve this equation. These 2 equations, there's one here, there's one a little lower. You've seen them a moment ago. I'll leave this work to you, but solve them. Bam. Here's VA, 17.9 meters per second. VB, minus 35.8, and the tension in the rope's 19.2 newtons. Now, as we go through these problems, I'm not going to go showing you all the algebra. It's a waste of time. I leave that to you to do. Now, when I hold off on this stuff, in my notes, I actually have the algebra. All right? But you need to be able to do this. So here's my point I'm getting at. If you ever if you play golf, a lot of people, when they play golf, if they get the ball within 3 feet of the hole, they say, oh, it's a gimme, and they just pick the ball up. And then watch them play in the tournament and they can't hit a 3-foot putt. All right. I strongly suggest as we go through this course, the problems I'm doing here, take the time to set them up and do them yourself and do the algebra. If you have trouble getting to this point, contact me. We need to talk, and we can go over things. So take the time. I'm not going to take the time in the video to show algebra, which you've already had, but make sure you can do it. All right, a few more introductory problems. So what do we have here? So we've got a worker that has a safety belt on, okay? And so here's this rope tied to him, and the rope has 4 feet of slack. Translated, he can fall 4 feet, all right? So what we want to do is suppose bad things happen, and this person falls, all right? It's kind of ugly, isn't it? So I want to find the average impulse force. The second you see that word, it's a momentum problem for a 4-foot fall. Okay? And to get that average impulse, we're being told the impulse duration is 0.6 seconds. So what that's basically saying is I'm going to have this average impulse times 0.6 seconds as being my integral for the impulse. All right, now let's think about this. What's going to be happening? This person is up here, and that's like state 1. Then they fall, and they're going to fall 4 feet, okay, taking up all the slack. So I'm going to call state 2 to be just before the impulse, okay? As there's no slack in the rope. State 3, that'll be after the impulse, okay? So in this problem, they're going to fall 4 feet before we get to this part, okay? You can't just go do this part. You actually have to let them fall, and we need to figure out how fast they're falling just before the rope catches them. Now, after the rope catches them, that's what's causing the impulse. What's their velocity going to be then? Well, we're assuming the rope doesn't break. Their velocity will be 0. They'll be hanging in the sky. They'll be scared like crazy, but they're alive. That's a good thing. So, here's what we have. They fall off this platform. They're going to fall 4 feet. And state 2 is just before the impulse. State 3 is post-impulse. So this is where, between 2 and 3 is where we're going to do our momentum problem. But we've got to figure out, we've got to get from here to there. So let's think about that for a second. When I start here, when I fall, what's the velocity going to be? 0. The vertical velocity, as you just kind of come off the edge, will start from 0, and then they'll accelerate. They're going to get to a velocity just before the rope stops them and the impulse happens, and they're going to fall 4 feet. That's an energy problem. Velocity, distance. So let's take that on. So we got to find state 2, 4-foot fall leading to velocity at state 2. So we've seen a lot of these things before, so let's just take a look at that. Energy is kinetic plus potential state 1, kinetic plus potential state 2. We start from rest, fall 4 feet. So initially, our potential energy would be, it's a 180-pound person, 4 feet higher at the start. Therefore, V2 becomes 0. That's fine. We could have made this 0 and put 180 times minus 4 out here. All the same. Then the question is how fast are they going? 1/2 m, 180 on 32.2, v squared. Solve for v. Going down at 16 feet per second, roughly. All right, now that we have that, we can go momentum from 2 to 3. So here's our momentum equation. So we know this. Here's our initial momentum. So we'll substitute that in. We know that after the impulse, velocity is 0, so we know what that is. And so what this thing is saying is we want to replace this integral with a average impulse force. So that's what's kind of like a constant times the duration, t, which is 0.6 seconds. Okay? So we'll just let that come in. So here's the mass. There's the velocity. The average impulse force times 0.6 is 0. Solve for that. and it's about 150 pounds. All right, so we're going to stop there and give you a break. And when you're ready, I invite you to come back for more.